Okay, when we last left off, we were discussing electron configurations and orbital box diagrams. Let's start off today's lecture by reviewing an example and working through an example. So first and foremost, we're asked to write the electron configuration for sulfur 2-. So looking up sulfur in the periodic table, so looking up sulfur's atomic number. Let's go to the periodic table. Sulfur's atomic number is 16. So our number of electrons is equal to our atomic number minus the charge. So for sulfur 2-, we have 18 electrons. Now we're going to arrange our orbitals in terms of increasing energy. And now let's fill our orbitals with electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, perfect. So now what we're going to do is we're going to write out our configuration by noting the number of electrons found in each orbital. So it would be 1s2, 2s2, 2p6, 3s2, 3p6. So this is the complete electron configuration for sulfur. Any questions on this example? Okay, so let's now work on the following example where we're asked to write an electron configuration and an orbital diagram for calcium. Let's spend about 3 to 4 minutes on this example, and then we'll discuss momentarily. And the electron configuration that I see in the chat looks great so far. And we'll discuss this example in another 1.5 to 2 minutes. Okay, so let's discuss this example. So if we go to the periodic table and we find calcium, calcium has an atomic number of 20. So we have 20 electrons to work with. We're then going to place our orbitals and draw our orbital box diagram, ranking our orbitals in terms of increasing energy. Let me move down so we have a little more space. So we have our 1s, 2s, 2p, 3s, 3p orbitals. So let's fill in our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. After filling the 3p orbital, we then fill our 4s orbital with the remaining 2 electrons. That in turn gives us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that's the complete electron configuration for calcium. Okay, so let's continue on and let's do another example. So in this case, we're asked to write the electron configuration for bromine and fill in an orbital diagram. Let's take about another 3 minutes on this example, and then we'll resume to discuss. Don't forget the fact that bromine, we are filling the d orbitals. So we'll discuss this example momentarily. And don't be shy to submit your proposed responses in the chat. And the responses I'm seeing so far look great in the chat. Let's spend about another 1.5 to 2 minutes, and then we'll discuss this example. And the responses I'm seeing in the chat look great so far, and we'll discuss in about another 1.5 minutes. Yeah, it's fine if you draw your orbital diagram horizontally as long as you're arranging the orbitals in order of increasing energy. Yeah. So let's discuss this example. So for bromine, so looking at bromine in the periodic table, so bromine has an atomic number of 35. So we have 35 electrons to work with. So drawing out our orbitals in order of increasing energy, we have the 1s, the 2s, the 2p, the 3s, the 3p, the 4s orbitals, not the 3d, and then after the 4s orbitals, only then do we have our 3d orbitals, and then finally we have our 4p orbitals. So let's add our electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 31, 32, 33. And then now that we've filled all of our empty degenerate orbitals, then we pair. So 34, 35. So we placed all of our electrons. Now we note the number of electrons in each of our subshells. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. There we go. So we've written out the complete configuration for bromine. Any questions on this example? Any questions on this example? Okay, let's do another example, and I'd like you to write the electron configuration this time for calcium 2+, and write a complete orbital diagram for calcium 2+. And we'll discuss this example in about another 3 minutes. And don't be shy to message in the chat your proposed responses and proposed electron configurations for the following ion, which is calcium 2+. And the responses I'm seeing in the chat look great so far. We'll discuss this example in about another minute and a half. Okay, so let's discuss this example. So calcium, so when we discussed calcium previously, we noted that neutral calcium has an atomic number of 20. To account for the 2+ charge, calcium 2+ has 20 minus 2, subtracting the charge from our total number of electrons. Calcium 2+ has 18 electrons. Let's now arrange our orbitals in order of increasing energy. So we have 1s, 2s, 2p, 3s, and 3p orbitals. We then place our electrons 2, 4, 6, 8, 10, 12, 14, 16, 18. So we placed all of our 18 electrons, and now we'll write out our configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6. So this is the configuration for calcium 2+. Any questions on this example? I saw in the chat someone wants me to scroll back up so they can write down the response from the previous question. So I'll do that at this time. Any questions I can address for these two examples? Any questions? Okay, so let's look at a way of reducing the workload that we have to do in order to write out electron configurations, and that's utilizing this idea of abbreviated electron configurations. So what we're going to do is we're going to sort our electrons into inner shell, otherwise known as core electrons, and outer shell or valence electrons. And what we're going to do is we're going to abbreviate the core electrons using the configuration of the closest noble gas configuration filled before your element or ion. So you may ask, well, what are core and valence electrons? Well, valence electrons are defined as the electrons in the outermost energy level, those with the largest N. These are the electrons farthest from our nucleus. Now, the number of valence electrons equals the group number for group A elements. Note one thing that's really important to keep in mind: D and F orbital electrons are not valence electrons. They're inner shell electrons. Okay, so to show how this works in practice, so if we look at lithium, our core electrons are our 1s electrons, while our valence electrons are the 2s electrons, because the electrons in that shell are found in the orbital with the largest N value. These are the electrons farthest from the nucleus. Now, the closest preceding noble gas, the closest noble gas before lithium is helium, which can be written as 1s2. So then we can abbreviate the 1s2, the inner shell or the core electrons, using the noble gas configuration of helium. Likewise, for example, if we're looking at fluorine, which is written as, in a longhand sense, 1s2, 2s2, 2p5, our 2s and 2p electrons are valence electrons. So we see that we have 7 valence electrons, which matches our group number of 7a. And just like before, we're going to abbreviate our core electrons using the electron configuration of the closest preceding noble gas. Now, the reason why we like to abbreviate our electron configurations is we're really interested in the valence electrons more than anything else, as those electrons are most reactive and are most relevant in terms of predicting bonding and ionization preferences. Okay, so let's take a moment and let's write the electron configuration for each element. So for oxygen, so longhand, oxygen's configuration would be 1s2, 2s2, 2p4. We're going to identify our valence electrons, and then we're going to abbreviate our core electrons using the closest preceding noble gas. Okay, so this would be helium, 2s2, 2p4. Okay, I'd like you now to take a moment and to attempt the following 2 examples and write the abbreviated electron configuration for that atom. And we'll discuss this example in about 4 to 5 minutes. Let's try to get some responses in the chat and then we'll discuss. And we already are starting to see some reasonable responses in the chat. It's quite good. And we'll discuss this example in another 4 minutes. And so the configurations I see in the chat look good, but let's try abbreviating the core electrons using a noble gas configuration. But the responses I'm seeing look good so far. Well, let's try writing abbreviated and practice writing abbreviated configurations by abbreviating the inner shell electrons using the closest preceding noble gas. And we'll discuss this example in about 2 to 3 minutes. Yep, and the responses I'm seeing in the chat look great so far. And we'll discuss this example in about 1.5 minutes. Okay, so let's discuss this example. So boron, our configuration will be 1s2, 2s2, 2p1. We can abbreviate our core electrons. Writing this out in an abbreviated configuration, we have helium, 2s2, 2p1. Notice that boron is a 3a element, so as a result, we have 3 valence electrons. For beryllium, the configuration is 1s2, 2s2. So we can write out this configuration as helium 2s2, noting that beryllium is a 2a element, and as a result, we have 2 valence electrons. Perfect. Let's do a few more examples. This time, let's try to write the electron configuration for a little more complicated elements. So for sodium, sodium has an atomic number of 11. So sodium would be 1s2, 2s2, 2p6, 3s1. Okay, we're going to now, if we look at the periodic table, so if we look at the periodic table, and we take a look at the periodic table for sodium, we notice immediately that the preceding element, the element right before sodium, is neon. So we can abbreviate these inner shell electrons as neon. And we can write our abbreviated configuration as neon 3s1. Now, one little trick that you could use to expedite writing your configuration, step 1, you find the noble gas directly before your element, and you write that here. Next, you know that the outermost n value would be equal to your period number, and we know that the number of valence electrons is equal to your group number, which is 1a. Since we have 1 valence electron, we fill our 1 valence electron into the 3s orbital. Now, of course, if we add more, we'd fill our s orbital followed by the p orbital. So this is our abbreviated configuration for sodium. Let's now take a look at aluminum. So aluminum is a 3a element, just like sodium. Aluminum has an atomic number of 13, and its core electrons can be represented by neon. Since we have 3 valence electrons and we're in the third row, we start by filling our 3s orbital, and then finally we fill our 3p orbital. That in turn gives us the following configuration for aluminum. This is an alternative method that's driven by looking at the periodic table, identifying your preceding element, and using the group number to calculate the number of valence electrons, and then filling the valence electrons in from the lowest to highest energy valence or outermost orbital. Any questions on these examples? Any questions on these examples? Okay, so let's take a moment and let's work on the following 2 examples, and let's try to write the electron configuration for the following two atoms. Either long form or abbreviated configurations would be expected. I'll ask explicitly for each exam question whether I want a long form or an abbreviated configuration. One thing that I want you to just keep in mind for these 2 examples is that d electrons are not valence electrons, but if you need to write them out. Show d electrons not found in your noble gas. So if your noble gas configuration doesn't include a certain number of d electrons, make sure you're explicitly stating the number of electrons in the d subshell. So we'll work on this example for about 4 to 5 minutes, and then we'll discuss. And the responses I'm seeing in the chat look great so far. And we'll discuss this example in about another 3 to 4 minutes. It's really good to see everyone picking up on this process and writing out the electron configurations efficiently. And let's try to get a few more responses in the chat, and then we'll discuss. Okay, so let's discuss this example. So if we look at chlorine, the long form configuration is chlorine has 17 electrons, would be 1s2, 2s2, 2p6, 3s2, 3p5. So we can abbreviate our core electrons as neon. So we'd write our abbreviated configuration as neon 3s2, 3p5. Perfect. So for bromine with a 35 electrons, we've seen our configuration was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now we have to fill the d orbital, 3d10, 4p5. Now in terms of the core electrons that we can abbreviate with a noble gas, we can abbreviate all of our n equals 3 and below electrons except for our 3d electrons. And we can abbreviate our core electrons as argon, and we note all of our core and valence electrons not found or abbreviated by argon as follows. So we write out 4s2, 3d10, and 4p5. So even though the 3d10 electrons, even though our d orbital electrons are technically core electrons, we still have to write them out because argon does not have 10d electrons in its 3d orbital. Does that make sense to everyone? So argon can only abbreviate up to the 3p6 electrons. All the other electrons we have to explicitly write out in our abbreviated configuration because those are not found in argon and those electrons are found in the electron configuration for bromine. Any questions on these examples? Any questions on these examples? Okay, so let's take a moment and let's try to write the electron configuration for each set of ions. For O2 minus, our number of electrons is equal to, so oxygen, we have an atomic number of 8, so we have 8 minus -2, which gives us 10 electrons. Okay, so now we're going to fill our electron configurations from the lowest to highest energy orbital. So we have 1s2, 2s2, 2p6. Okay, and we can abbreviate this configuration as helium 2s2, 2p6, or you can write it in not a less technically correct, but commonly used shortcut of just saying neon. The configuration of neon would also again be helium 2s2, 2p6, or you can just write it as neon. I've seen both methods used, although the method involving helium is a little bit more correct. I'd like you now to take a moment and write the configuration and the abbreviated configuration for the following set of 3 ions. And we'll discuss this example in about 4 minutes. And don't be shy to submit your proposed electron configurations for each of these ions. And remember, as we discussed previously, the electron configuration for an ion will overwhelmingly match that of a noble gas configuration. So let's try to write the configuration for these three ions, and then we'll discuss in about 3 to 4 minutes. And the responses I see in the chat look good. Let's try to get a few more responses and we'll discuss shortly. And we'll discuss this example in about another 2 minutes. Okay, so let's look at this example. So sodium plus has 11 minus 1, which is 10 electrons. So one trick that you can do is you can look at the periodic table and look for the element that has the same number of electrons. So we know neon has 10 electrons, so we can write the configuration for sodium plus as equivalent to that of neon, which would be helium 2s2 2p6. Likewise, another way of thinking about this is for aluminum 3+, you can go and find aluminum in your periodic table. And what you can do when you're looking at your periodic table is for each positive charge, for each electron lost, you count one space to the left. So since we have a charge of +3, we count 3 spaces to the left, and that gives us for aluminum 3+ that we have a configuration of neon. In other words, helium 2s2 2p6. We can also show that aluminum 3+ has 13 minus 3, or 10 electrons to its name. For lithium plus, so looking at our lithium plus example, we have helium followed by lithium. Since we have a +1 charge, we can go to our periodic table and just count back one space, since we've lost one electron. So then the configuration for lithium plus would match that of helium. You can also think of it as lithium plus has 3 minus 1 or 2 electrons. So lithium plus would be equal to a configuration of 1s2, which matches the configuration of helium. However you want to think about it, all of those methods are valid. Any questions on this example? Do these make sense so far? Yes, yes. I'll be specific on whether I want you to write an abbreviated or a full configuration, though I have a strong preference, and the most common configurations that you'll be asked to write would be abbreviated configurations, just because they're operationally, they take less time to write. Okay, let's keep going now. And let's talk a little bit about valence electrons. So valence electrons are the electrons in the outermost energy level, the largest N. These are the electrons farthest from the nucleus. The number of valence electrons is equal to the group number for main group elements. And what's really interesting is that elements of the same group in the same column have the same valence electron configurations and the same number of valence electrons. This is important because valence electrons participate in chemical reactions and bonding. Thus, elements of the same group have similar reactivity because they have the same valence electron configuration and the same number of valence electrons. So we can see this here, that as we move down a column, the electron configuration for the valence electrons remain the same, but your N value increases. As you move to the right across your periodic table, the number of valence electrons increases. Note one thing that you have to be really careful about. D and F orbital electrons are not valence electrons. They're considered core electrons. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Okay. So let's talk about another term, isoelectronic species. We may have heard this term all the way back in chapter 2, but just as a reminder, isoelectronic species have the same number of electrons and thus the same electron configuration. So for example, sodium plus has 10 electrons. Fluorine minus or fluoride has 10 electrons. O2 minus has 10 electrons. N3 minus also has 10 electrons. So all of these ions have the configuration of neon. So all of these ions are isoelectronic with the noble gas of neon. Isoelectronic species have the same number of electrons, the same ground state electron configuration, and in general, they exhibit very similar reactivity in terms of sharing of electrons, gain or loss of electrons. Does this idea make sense to everyone? Any questions on isoelectronic species? Okay, I'd like us now to take a moment and try to answer the following question. What neutral atom is isoelectronic with H minus? So what neutral atom has the same number of electrons as H minus or hydride? Helium, exactly right. So if we look in the periodic table for an element with 2 electrons, that matches helium. So we say that hydride is isoelectronic with helium. Does this make sense to everyone so far? Okay, so let's keep going. So noble gases are a really critical group in the periodic table to help us understand ionization preferences and understand bonding preferences. So noble gases have a full outermost valence shell and in general are more stable and less reactive than other electron configurations. So noble gas configurations are relatively stable. A full shell is relatively stable. This can either be 8 valence electrons or a 1s2 configuration in the case of helium. Now, the reason why this is important, it's more favorable for atoms to gain or lose electrons if you generate a stable noble gas configuration. Further, it is relatively easy to lose high energy valence electrons or to gain electrons to create a full outermost valence orbital. Thus, we now have a more substantive justification for the rule that we learned all the way back in chapter 3, that atoms form ions with a noble gas configuration, and atoms like to form cations with charge equal to the group number. For group 1a through 3a elements, we are losing electrons, while atoms like to form anions with charge equal to the group number -8 for group 5a through 7a elements. In this case, we are gaining electrons. So let's look at an example. So aluminum is a group 3a element. It prefers to form aluminum 3+. The reason for that is we have 3 valence electron. So in order to reach a noble gas configuration, we are losing our 3 valence electrons. That's why aluminum adopts a 3+ charge, because we need to lose 3 valence electrons to form a stable noble gas configuration. Likewise, oxygen forms O2- because initially we have a configuration of 2s2, 2p4, where we have 6 valence electrons. So we need to gain 2 electrons. So by gaining 2 valence electrons during ionization, we can generate a noble gas configuration for our oxygen anion. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions? Okay, so with that in mind, let's try to write the abbreviated or noble gas electron configuration for the following ions. So I'll start us off. O2-, we have 10 electrons. So that matches the noble gas configuration for neon. Let's take a moment and let's try to write the noble gas configuration for the following elements. And more specifically, the ions of the following elements. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to message me in the chat with your proposed responses for the noble gas configuration for the following two ions. And the responses I see in the chat look great so far, and we'll discuss in approximately another minute. Okay, so potassium plus. So counting the electrons, potassium in the periodic table has 19 electrons, -1 for the +1 charge. So we have 18 electrons. The noble gas that has 18 electrons, that potassium plus is isoelectronic with argon. Lanthanum 3 plus, it's quite an interesting metal. So we naturally have 57 electrons. We have a 3 plus charge, so we subtract 3. That gives us 54 electrons. So lanthanum 3 plus, looking at the noble gas with 54 electrons, that matches the configuration of xenon. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Any questions? If not, let's take a look at the following example where we're asked to predict the charge and electron configuration of the ion formed from the following elements. So I'll start us off. Phosphorus has 15 electrons and is a group 5A element. The predicted theoretical charge of phosphorus would be equal to 5A minus 8, which gives us a charge of -3. So for P3 minus, we'd have 15 minus -3. In other words, we'd have 18 electrons. And for 18 electrons, that would correspond to the electron configuration of argon. Does this example make sense to everyone so far? Okay, let's take a look at the following 3 additional elements, and let's try to write out the electron configuration and the preferred ion. Let's try to write out the preferred ion formed from each of these atoms. And then I'd like you to write the configuration of that ion formed. And just make sure you're careful with noting whether the charge is positive or negative. And the responses I'm seeing in the chat look great so far, and we'll discuss in about another 3 minutes. and we'll discuss this example in another 2 minutes. Let's try to get a few more responses in the chat, and if you have any questions, don't be shy to message me in the chat with your questions or proposed responses, or you can unmute and ask your questions verbally. Okay, so the responses I see in the chat look great so far. So let's take a look. So aluminum is a 3A element. So the charge predicted would be equal to +3. Aluminum 3+ has 13 minus 3 or 10 electrons. So aluminum 3+ has a configuration matching that of neon. Okay, scandium is a bit of a weird case. So if we think about scandium, so looking at scandium in the periodic table, it's not formally a main group element, but if we think about scandium and look at its location in the periodic table, scandium is 3 spaces away from our noble gas and it's a metal. So if we wanted to lose our valence electrons and generate a noble gas configuration, so looking at scandium, its baseline configuration would be argon 4s2 3d1. To reach a noble gas configuration, we'd have to lose our valence electrons, and that would give us a configuration for scandium 3+ of argon. So in general, metals prefer to lose their valence electrons to form a cation with a noble gas configuration, especially your early stage metals, including early stage transition metals. For iodine, so iodine is a group 7A element, so the charge predicted for iodine is 7 minus 8 or -1. So for I-, we'd expect 53 minus -1, which gives us 54 electrons. So then for iodide, I-, that would match the configuration of xenon. Does this example make sense to everyone so far? Any questions on this example? Okay, so let's discuss and let's focus in on the d and f orbital electrons. So, as we noted, the 3d orbital is higher in energy than the 4s orbital. Now this gap varies for each element, but in general, and note this key word here, the empty s orbital is lower in energy than the d orbital. And the reason for that, as we discussed, was orbital penetration. The s orbital is more readily able to access regions closer to the nucleus and experience a greater stabilizing effect from the nuclear charge. Okay. Now, Where things get a little weird is that when we start looking at transition metals, we see often irregular electron configurations. So thinking about the gap between the s and d orbitals, this gap is dynamic and depends on the element that you're looking at, the nuclear charge, and many other factors. Now, in some cases for transition metals, and this is specific to transition metals, the energetic cost of pairing electrons may be less than the energetic cost to place the electron in a higher energy d orbital. Okay, so for example, copper can form this really odd configuration of 4s1, 3d10. So overwhelmingly, we see that these irregular configurations occur when you generate a D5 or D10 configuration. But there are exceptions. Now, I'm not expecting you to know all of the weird exceptions like for ruthenium. What I am expecting you to know is that if you're given a transition metal that can form an irregular configuration that is either D5 or D10, then you will be expected to write the irregular configuration. So copper, chromium, molybdenum, palladium, those are all fair games because they follow the D5 and D10 trend. For some of the odder exceptions, I'm not expecting you to memorize them. Does that make sense to everyone? What my expectations are and the fact that we do see irregular configurations due to the fact that there's this push-pull dynamic between pairing electrons versus placing the electrons in the slightly higher energy d orbital. So for example, for chromium, rather than having to pair our electrons in our s orbital, we instead place each of our electrons in empty d orbitals. So this is the correct configuration for chromium versus the expected configuration. And the reason for that, again, just to emphasize, is that the pairing energy is greater than the difference in energy between the s and d orbitals. And this only occurs for transition metals and transition metal elements because the gap between the 4s and 3d orbitals are quite small for transition metals. So it's not as much of a penalty to promote that electron to the higher energy orbital. This logic only applies to transition metals, okay? And this is why we can see irregular configurations for transition metals. Yes, essentially it costs less energy to dump that electron into an empty d orbital or promote that electron to a d orbital rather than pair electrons in our s orbital. That's exactly right. Okay, so this phenomena can also be observed for d and f orbitals, but that's a topic for later classes. Now, on this note, let's focus on transition metal ionization. So when we ionize transition metals, the s orbital electrons are removed first. Now, of course, you can just memorize this rule, but if we think about what's going on here, that sentence is a little strange, right? We know most transition metals have a stable metal 2+ ion, but the fact that we're removing the s orbital electrons first, this implies that the s orbital electrons are higher in energy than the d orbital electrons. Now, the way that I like to think about it, the way I like to think about this and resolve this contradiction is that the relative energy of your 4s and 3d orbitals change when electrons are placed in that orbital. Okay, and filling an s orbital with an electron pair costs energy. Further, when you start to fill your d orbital, you introduce a small shielding effect. And in turn, what that means is when you fill the d orbital, you're increasing the energy of the s orbital electrons. So, in turn, what that means is that it's preferred during ionization for you to lose your s orbital electrons preferentially. Now, again, this relative energy between the s and d orbital electrons varies depending on the element. The other way that I like to think about this idea in ionization is that electrons can be removed from the most accessible outermost orbital. And since the s orbital electrons are the farthest away from the nucleus, are the most accessible, they're the most readily lost electrons. So just to keep things short, sweet, and to the point, transition metals typically lose the outermost highest energy s orbital electrons to give cations. So for example, cobalt will lose its 4s electrons. Now, it's important during ionization to just lose the s electrons if you're predicting the 2+ ion. Don't do anything fancy and try to rearrange this configuration into an irregular configuration. For ionization, you first and foremost lose your s electrons, and then you start to lose your d electrons. This can occur when you're looking at something like manganese or other early stage transition metals, where we have the loss of the outermost s and d orbital electrons during ionization. So manganese, for example, has a large number of valence electrons. So manganese has a configuration of argon, 4s, 1, 2, 3, 4, 5, 4s2, 3d5. So during ionization, we can lose our 7 valence, quote unquote, valence electrons and generate manganese 7+, which has a configuration of argon. You may notice above manganese, you'll see the symbol 7B. Some of the symbols for transition metals serve to indicate ionization preferences. That's why the numbers aren't always necessarily in order for your transition metals. Okay. Now, before we leave off on this topic, I just want to put a note here. And I just want to say, do not write irregular configurations for transition metal ions. Now, this may seem very tempting at first glance. So for example, iron has a configuration of argon, 4s, 2, 3d6. Okay? During ionization to generate iron 3 plus, oh sorry, let's look at iron 2 plus. So if we're ionizing to generate iron 2 plus, we would just lose our s orbital electrons, our highest energy, most accessible electrons, to give us the configuration of argon 3d6. Iron 2 plus is not argon 4s1 3d5. The irregular configuration rule and the S5, sorry, the D5, D10 rule only applies to neutral transition metals. During ionization, the charge and effective nuclear charge changes, and as a result, irregular configurations are substantially less common for transition metal ions that we see in this class. Does that make sense to everyone? So for transition metal ionization, keep it as simple as possible. Lose 2 of your s electrons, and then if you're undergoing further ionization, then you lose your d orbital electrons. You only have to worry about irregular configurations for the neutral transition metals. Yes, at least for the purposes of this class. Okay, continuing on, let's talk a little bit about magnetism. So magnetism is evidence of electron spin. So atoms with unpaired electrons are attracted to external magnetic fields, and those with completely closed or full subshells are repelled. Substances with unpaired electrons that are attracted to magnets are known as paramagnetic, while substances with no unpaired electrons that are not attracted to magnets are said to be diamagnetic. This is the same reason why there are giant signs not to take copper metal, copper carts, or copper tanks anywhere near an MRI or NMR machine, because it'll immediately, as copper is a paramagnetic material, it'll immediately be attracted to the magnet. So if only people would review and learn the idea of paramagnetism, we maybe could avoid some of these very embarrassing and expensive accidents. So thinking about copper, so looking at copper, let's just write our normal configuration, pretending that irregular configurations aren't a problem just yet. So we'd have argon, 4s2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9. Copper can form a D10 configuration, so copper is an exception. It can form argon, 4s1, 3d10. So if we look at the configuration for copper, we see that if we look at our 4s and our 3d orbitals, filling in our orbital diagram, we see very clearly that copper has an unpaired electron, making copper paramagnetic. Does that make sense to everyone so far? So copper adopts an irregular configuration. It has an unpaired electron, and as a result is paramagnetic. This is neutral copper metal. Okay, so with this example established, I'd like you to use orbital diagrams to show whether zinc 2 plus or titanium is paramagnetic. So you'd have to write out the configuration and orbital diagram. Keep in mind that you only really have to care about your valence electrons. So you don't need to write a full orbital diagram. just an orbital diagram for your valence electrons. So let's use this orbital diagram to show whether zinc or titanium is paramagnetic, whether we have unpaired electrons. And the responses I see in the chat look great so far. And we'll discuss this example in another 2 to 3 minutes. And I would check to make sure that for zinc, you're writing out the correct configuration for the zinc 2+. Keeping in mind that irregular configurations are only typically common for neutral transition metals. And we'll discuss this example in another 2 to 3 minutes. And don't be shy to submit your responses in the chat. Only one of these species is paramagnetic, just as a hint. Okay, so let's discuss this example. So this is a multifaceted problem. It's a great exam question. And the responses I'm seeing in the chat are wonderful. It's quite encouraging to see. So for zinc, whoops, one moment. Sorry about that. There's a mild delay in one note. So zinc has a configuration of argon, 4s2, 3d10. Okay. Zinc, when it loses electrons to form zinc 2+, will lose its s electrons first. Zinc 2+ will have the configuration of argon 3d10. Okay, so drawing out that diagram, we'll draw out the diagrams in a moment. Let's look next at titanium. So titanium has the configuration of argon 4s2 3d2. Okay, so let's look at the configuration of titanium and zinc 2+ from an orbital diagram perspective. So titanium looks like first we pair our 4s electrons and then we fill our empty 3d orbitals preferentially. As we can see for titanium, we have 2 unpaired electrons, so titanium is paramagnetic. To serve as a counterpoint, zinc 2+ has 10 d electrons. Zinc 2+ has no unpaired electrons, and as a result, zinc 2+ is known as diamagnetic. Does this make sense to everyone so far? Let me see. Oh, because it's an ion, we lose our s electrons first. And just because something is an ion, for transition metals, they prefer to lose their s electrons. And just because it's ionizing doesn't mean we're losing all of the electrons. We're just losing the outermost, highest energy electrons in most cases. Zinc 2+ is also a relatively stable ion because it has a D10 configuration, and D10 configurations or full shell or subshell configurations are generally quite stable. Did that answer your question? Perfect. So now we're really good at writing configurations of atoms and ions. Let's talk next about periodic trends. How are properties and reactivity tied to electron configurations and the location of elements on the periodic table? So the majority of periodic trends are underpinned, so periodic trends such as atomic radius, ionization energy, and electron affinity are dictated by the nuclear charge and the outermost valence electrons. So the electrons in the valence orbitals are attracted to the protons in the nucleus, and they are repelled by our inner shell electrons. So there's this push-pull dynamic. So there's this push-pull dynamic again between shielding and our nuclear charge. So our outermost electrons, or our valence electrons, experience an interplay between attraction to the nucleus and repulsion from our innermost or inner shell electrons. And again, we've summarized the amount of effective nuclear charge, the amount of nuclear charge that our electron actually experiences using the effective nuclear charge expression. So where effective nuclear charge is a description of the net positive charge experienced by an outermost electron in a given atom, accounting for inner electron shielding effects. As we notice, effective nuclear charge increases as you move right across a row. We're adding more protons, right? More protons, more positive charge, greater effective nuclear charge. Effective nuclear charge also increases as you move down a column, but there is a reset and there's a strong drop where effective nuclear charge decreases when you start filling a new row, otherwise known as a period. The reason for that is looking, for example, from going from neon, let's go from hydrogen, from helium to lithium. Okay, so helium, we have 2 electrons in our 1s orbital. So here's our nucleus, our 1s electrons are somewhere around here, and we have 2 electrons. When we go to lithium, as we notice, when we start to fill a new shell, this electron experiences a strong shielding effect. Because our previous shell, which is now our inner shell, has a large number of electrons that are shielding our outermost electron from the nuclear charge. So each time you start a new period in the periodic table, your effective nuclear charge drops precipitously. Does that make sense to everyone? So for effective nuclear charge, I like to draw an arrow. I like to remember things by drawing arrows. So effective nuclear charge is an arrow going down and to the right. It increases going down and to the right. So don't be shy when you have your exam periodic table and you open up your exam with your fresh periodic table, just draw the arrow immediately and label it. It's a nice little mnemonic, saves you time, saves you energy. Or you can count the atomic number and say, well, more protons, greater effective nuclear charge. Either method is fine. All of the periodic trends that we are going to discuss are underpinned by this concept of effective nuclear charge. Okay, so let's keep going now. So let's talk about atomic radius. So there are 2 ways of looking at atomic radius. Van der Waal, where we have 2 atoms not bonded. So van der Waal is not bonded. While your covalent radius is looking at 2 bonded atoms and the distance between the nuclei for 2 bonded atoms. So depending on what book you're reading, it will either give you the van der Waal or the covalent radius. The covalent radius is a little bit more influenced by other factors associated with the nature of your chemical bond, but nonetheless, we have a swath of experimental data on bond lengths and bond strengths or bond enthalpies. Now let's try to rationalize our atomic radius data. Let's try to rationalize the data that we have on the atomic radius of our atoms using electron configurations and Coulomb's law. So first, the electrons in valence orbitals are attracted to the protons in the nucleus and repelled by electrons in the inner shell orbitals. Now, as the valence electrons are farthest from the nucleus, the farthest out electrons, the valence electrons, dictate your atomic radius. So the outermost valence electrons determine your atomic radius. And the forces and the attractive and repulsive forces acting on that outermost set of electrons is dependent on the nuclear charge and shielding effects. Now, what's nice is that electrons in the same orbital shell, so same n value, do not contribute substantially to shielding. So for example, 2s electrons do not really shield 2p electrons. So let's just draw a picture just to help us visualize that. And this is going to be a bit of a It's not going to be super perfect, but so for example, here are our 2s electrons, okay? And our 2p orbital is going to extend outward about the same distance. So we have 3 2p orbitals. And because the 2s and 2p electrons are about the same distance from the nucleus, they do not substantially shield each other. But I do want to say electrons still repel each other. So these still are negatively charged species, so we have to respect that. Does this make sense to everyone so far? Any questions so far? Okay, so let's look at periodic trends for atomic radius. So here's a chart for atomic radius. Okay, and I'm just going to put some labels. So 1, 2, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. Okay, so my question to all of you is, what do we observe? What do we observe for this graph of radius versus atomic number? What do we see as we move down the periodic table? As we increase our n, as we go farther down the periodic table, as our atomic number increases, as we go down a column, what is happening to our radius? As our n increases, what happens to our radius? As we move down the periodic table, yep, as we go down the periodic table, our atomic radius gets larger. Okay, larger n, larger atom. Wonderful, okay? So that's our first thing that we need to note. Let's give it one moment. There's a mild delay. Oops, sorry about that. Sometimes OneNote experiences a small delay. Okay, so our first major trend that we've noted, as we move down a group or column, our atomic radius increases. This makes sense. This makes sense. We can understand what's going on here. Because increasing n leads to a larger orbital size and a larger atomic radius. That's why we can see, for example, that nitrogen, which is n is equal to 2, is smaller than phosphorus, which is n is equal to 3. Likewise, hydrogen, which is n is equal to 1, is smaller than lithium, which is n is equal to 2. Now let's go up and let's look at our chart. What happens as we move to the right across a row? As we go from lithium to neon, what happens to our atomic radius? As we move to the right across a row or a period, yes, exactly right. Our atomic radius decreases. So that's our next major conclusion. As we move right across a row or period, our atomic radius decreases. Well, why is that? As we move right across the row, we are increasing our nuclear charge, and we have more protons in the nucleus. So the way that I like to remember atomic radius, is I write the word increasing atomic radius. and I draw an arrow going down and to the left. So this is another mnemonic to help you remember. So just as a refresher, looking at our chart, atomic radius increases as you move down the periodic table and decreases as you move to the right. This is why, for example, lithium, which has an atomic number of 3, which means it has 3 protons, is larger than fluorine, which has an atomic number of, let me look that up in the periodic table really quickly, which has an atomic number of 9, or 9 protons. Fluorine has more protons, and as a result, it has a greater nuclear charge. And that larger nuclear charge is more readily able to attract our external, our valence electrons. So again, just to show this difference, so for hydrogen and lithium, so in our 1s orbital, our 1s orbital is much smaller than a 2s orbital. Comparing lithium and fluorine, if we have 3 protons, our effective nuclear charge is going to be smaller than if we had 9 protons. Okay, so looking at the question in the chat, lithium has a greater atomic radius than fluorine. That's correct. You're asking, what about phosphorus? So phosphorus would have a larger atomic radius than fluorine, but I would caution you when you're comparing across rows in the periodic table and across columns, that these rules often get mixed together, and you can often end up with results that these very simplistic rules can't fully explain. So I would caution against comparing 2 elements in different columns and different rows in the periodic table, as the comparisons become a lot less clean, as there are a lot of factors that you have to consider in terms of nuclear charge, orbital size, electron repulsions, and that's covered in much more detail in an inorganic chemistry course. You will have to compare 2 elements in the same group and 2 elements in the same row. Yeah, so you'd just be applying these rules and applying concepts associated with effective nuclear charge and other periodic trends that we've discussed to answer questions, just like we've done in these examples. Does that make sense? Okay, so just as a refresher, so to continue to go through this, allow me one moment just to reset OneNote. Okay, so just talking about a refresher for the periodic trends for atomic radius. As you move right across a row, nuclear charge increases. We're adding protons. As nuclear charge increases, our atomic radius decreases. In other words, as you move right across a row, the atomic radius decreases. This keeps going until you begin a new period or a shell. Because you're filling an empty outermost orbital, you see a large increase in atomic radius. So in summary, looking at this chart, atomic radius increases as you move down a group, and it decreases as you move right across a row or period. So let's apply what we've learned, and let's try to predict which of the following elements in each of these pairs would have the largest atomic radius. So comparing sodium and potassium, so sodium is n equals 2, potassium is, sodium is n equals 3, potassium is n equals 4. Larger n leads to a larger radius. So we'd expect potassium to be larger. I'd like you now to attempt the following two examples and predict which of the following elements would have the larger atomic radius. And then we'll discuss this example in about 3 minutes. And the responses I see in the chat look great so far. Let's try to get a few more responses in the chat, and we'll discuss in about another 1.5 to 2 minutes. And the responses I see in the chat look great so far. So let's discuss. So if we compare carbon and nitrogen, nitrogen is farther to the right on the periodic table, and as a result, carbon is larger than nitrogen. Likewise, if we compare silicon and chlorine, chlorine is farther to the right in the periodic table, it has more protons and a greater effective nuclear charge, and as a result, chlorine is smaller and silicon is larger than chlorine. Do these examples make sense to everyone so far?
Hey, Professor?
Yes.
Can you please explain that again? I'm kind of confused.
So, atomic radius decreases as you move right across a row, right? Since carbon is farther to the right, since nitrogen is farther to the right, nitrogen is smaller, and thus, by extension, carbon is larger.
Okay.
Does that make sense?
Yeah.
Perfect. Do you have another question that I can address?
No, that's it. Thank you.
Okay, perfect. We'll be doing some more practice on this just to make sure we're comfortable with predicting atomic radius and comparing atomic radius. Any other questions I can address? If not, we'll focus on the next few examples. Okay, so in the following problem set, we're asked to write the electron configuration for each element and indicate which atom has a larger atomic radius. So I'll start us off. So hydrogen and lithium. So hydrogen's configuration is 1s1. Lithium's configuration is helium 2s1. Hydrogen is n equals 1. Lithium is n is equal to 2. So then lithium is larger as its outermost orbital is larger. Okay, so let's take a look at the following 3 examples. I'd like you to write the configuration for each of these atoms, and then I'd like you to predict which atom would have the larger atomic radius. N represents the orbital size, the principal quantum number, and N also represents the period number or the row number in the periodic table. And the period number or row number in the periodic table is directly tied to atomic radius. As you increase your period number, as you increase N, your atomic radius also increases a commensurate amount. Does that make sense? Perfect. And don't be shy to submit your responses for these 3 questions, and then we'll discuss in about 3 to 4 minutes. And we'll discuss this example in another 1.5 to 2 minutes. Let's try to get a few responses into which atom in each of these pairs has the larger atomic radius. I'd like to see a few responses before we discuss, or at the very least, don't be shy to ask questions in the chat or unmute and ask your questions verbally. and we'll discuss in about another minute and a half. Let's try to get a few more responses. Try to get a few responses in the chat. And then we'll discuss momentarily. Okay, so let's discuss, and I'm going to have the class chime in to help me out. So for oxygen and fluorine, oxygen's configuration is 1s2, 2s2, 2p4. Would someone like to help me out and contribute the configuration for fluorine? Now, one trick to keep in mind is that fluorine is right next door to oxygen and is one space to the right, or one additional electron. So would someone like to provide me the configuration for fluorine? Would someone like to provide me the configuration? Yep, perfect. We have helium, 2s2, 2p5. So a quick way to get the configuration for fluorine is just add an electron to the configuration of oxygen. Another way of thinking about things. Now, if we compare oxygen and fluorine, oxygen has an atomic number of 8, so we have 8 protons, while fluorine has an atomic number of 9, so we have 9 protons. So since these elements are in the same row and fluorine is to the right of oxygen, fluorine is smaller, ergo, oxygen is larger. So more protons, greater nuclear charge, farther to the right on the same row, smaller atom. Because fluorine is smaller, oxygen is larger. Does that make sense to everyone? Does that make sense? Perfect. So let's look at lithium and sodium. So lithium's configuration we've already seen is helium 2s1. Would someone like to volunteer the configuration for sodium? What's the configuration of sodium? Neon 3s1, exactly right. Okay, so looking at the outermost orbital end, the outermost orbital size, sodium has a larger outermost orbital, larger n, it's farther down on the periodic table, and as a result, we can conclude that sodium is larger. Okay. Let's look at chlorine and bromine. We've actually already written the configurations for chlorine and bromine. The configuration for chlorine is, let's check the periodic table just to be sure. Okay, so for chlorine, we have neon, 3s2, 3p5. For bromine, we have argon, 4s2, 3d10, 4p5. And I would look at the earlier section of the notes if you are curious how we obtained these two configurations for chlorine and bromine, as we did that in an earlier example. So chlorine is n equals 3, bromine is n equals 4. Bromine is farther down in the periodic table, and as a result, which atom is larger? Which element has the larger atomic radius? Bromine, exactly right. Exactly right. Bromine is farther down in the periodic table, and as a result, it has a larger atomic radius. So as a result, bromine is larger. Perfect. Any questions on these examples? If not, let's keep going and let's discuss atomic radius in the context of the D block elements. So atomic radius decreases as you move across the D block. That makes sense intuitively because just like any other trend, as you move right across the periodic table, you're increasing the number of protons and your atomic radius decreases. Now, this drop in atomic radius is pretty pronounced for the D block because the D orbital is closer to the nucleus than the S orbital. Because, for example, we have a 3D orbital versus a 4s orbital. Now, filling the D orbital as a result does not fill your valence orbital. Further, adding a proton to the nucleus increases the nuclear charge, leading to a decrease in atomic radius. Now, this is true for transition metals, except in one case. The atomic radius actually increases when you have a D10 configuration. And the reason for that is that the full d orbital effectively shields the outermost s electrons, leading to an increase in atomic radius. So for example, so if this is our nucleus and we have a few of our, let me draw out some d orbitals. Okay, so if we have an incomplete shell, so this is our 3d orbital and this is our 4s orbital. So our incomplete or our partially filled d orbital does not efficiently shield the 4s orbital electrons. However, when we have a completely full d orbital, when all of our d orbitals are completely filled, so a full d orbital shell or subshell shields the 4s electrons. And as a result, what we see is an increase in atomic radius as 4s electrons experience shielding. They're less able to experience the attractive interaction with our nucleus, and as a result, because these outermost electrons are experiencing this strong shielding effect, They experience a weaker attractive interaction with the nucleus, and as a result, our atomic radius increases. So d orbitals of the d subshell is not very effective at shielding unless it's completely full. And a D10, a D10 full d subshell can effectively shield the 4s electrons from the nucleus, and as a result, your atomic radius increases when you fill your d orbital completely. Does that make sense to everyone? Okay, and we can actually see this in the periodic table, and this is where we got the first inklings of D10 configurations. As you notice, silver, copper, zinc, cadmium, and palladium, we see this large increase in radius, and that's because we have D10 configurations. So we can actually see in our observed atomic radius for each element that atomic radius increases dramatically when we have a D10 configuration. But in general, as you move right across the periodic table, including through the D block, your atomic radius decreases. Does this make sense to everyone so far? Okay, so this is a nice little segue into our next idea, which is this idea of ionic radius. So let's start by talking about cations. So cations, quite simply, atoms will lose electrons to form cations. In the case of cation formation, the number of protons in the nuclear charge doesn't change. Now, removing electrons has two major effects. First and foremost, removing electrons can remove electrons in the outermost orbital, decreasing the atomic radius. So for example, in sodium, we have an inner shell, and then we have this outer shell containing our 3s orbital with one electron. And this is our inner shell of let's just say, neon. When we remove this outermost electron and we go to sodium plus, suddenly we don't have an electron in that orbital. So our outermost electrons, our outermost orbital, we're now concerned with our outermost 2s and 2p orbitals. So in effect, by removing our outermost electron, our atomic radius has decreased because we no longer have electrons in our outermost orbital, which is very large. Does that idea make sense? If you remove the outermost electron, you no longer have electrons in the large outermost orbital, so your radius shrinks, because now your outermost orbital is smaller and closer to the nucleus. Okay. Additionally, when we look at cations, cations in general have a smaller atomic radius as you have less electrons experiencing a relatively large nuclear attraction, and because we have less electrons, we also have less repulsive interactions. So in general, cations are smaller than their neutral elements, and atomic radius for cations decreases as your cation charge increases. So for example, looking at these few examples, as we go from lithium to lithium plus, as we see the atomic radius drop substantially. Why? So for lithium, we have a configuration of helium 2s1. For lithium plus, our configuration is just 1s2. So as we see, we went from an n equals 2 atom to an n equals 1 ion. We have a smaller outermost orbital, so our atomic radius shrinks accordingly. Now, if we compare lithium plus and beryllium 2 plus, we see that beryllium 2 plus has a configuration of 1s2. But if we compare lithium and beryllium, lithium has 3 protons while beryllium has 4 protons. Because beryllium has more protons and a greater nuclear charge, it has a smaller atomic radius. Does this make sense to everyone? The periodic trends for cation ionic radius. The radius in general decreases dramatically for cations, and the radius decreases even more dramatically the more electrons you remove and the greater your cation charge. Any questions so far? So let's keep going now and let's talk about ionic radius in the context of anions. So anions, let's talk about a few trends. First, adding electrons increases electron-electron repulsions, which lead to an increase in the atomic radius. Further, anions have a larger atomic radius as you have a large number of electrons experiencing a relatively small nuclear attraction because we haven't changed the number of protons, we've just piled on more electrons. The atomic radius for anions almost always increases, and it increases quite dramatically as your anion charge increases. Let me just check the question in the chat. Did I answer the question that was in the chat comparing lithium plus and beryllium 2 plus? Lithium plus is larger because it has less protons and a weaker nuclear attraction for its outermost electrons. Has a weaker nuclear charge. Did that answer your question? Perfect. So, looking at ionic radius, so in general, adding electrons increases your atomic radius, increases your ionic radius as you have more electron-electron repulsions, and we have a greater number of electrons experiencing the same amount of nuclear attraction, the same nuclear charge. So for example, looking at oxygen, we have neon 2s2 2p4, while O2 minus has a configuration of neon 2s2 2p6. Oxygen has 8 protons to its name, and oxygen 2 plus has the same 8 protons. So since we have more electrons that are they're experiencing repulsive interactions, and we have the same number of protons, our radius increases when we add additional electrons, when we form an anion. This effect is more pronounced when we have a larger charge because our relative number of electrons to protons becomes even more lopsided. So if we compare fluorine, which is neon 2s2 2p5, we notice fluorine has 9 protons. That's why fluorine is naturally in the neutral state, smaller than oxygen. If we think about F minus, has the configuration of neon 2s2 2p6. We still have 9 protons, but now we have 10 electrons. And because we have more electrons than protons, the electrons are experiencing greater repulsive interactions, and there's not really an increase in the nuclear charge. We have more electrons experiencing the same attractive interaction, and as a result, our radius increases. And the larger the charge, the more electrons we pile on, the greater our radius will increase by. Does this make sense? Yes? Is there a question I can address? Yes, O2 minus would in fact be larger, as we can see from this data set, because we have less protons, a weaker nuclear charge, and as a result, we have a larger atomic radius. Perfect. Okay, if we don't have any further questions, let's talk about a general rule set for predicting ionic radius. So in general, atomic radius will increase as you form anions, and your radius will decrease as you form cations. As a general rule to shortcut estimating the radius of an ion, first, I want you to try comparing your ion to their isoelectronic neutral element. So first, you check the electron configuration of the ion. You find the element with the same electron configuration. It will almost always be a noble gas in most cases. And then I want you to examine whether the nucleus has more or less protons. So your goal is to count the number of protons and compare your isoelectronic element to your cation or anion. So for example, sodium plus has the same configuration as neon. Sodium has 11 protons, neon has 10 protons. Thus, because sodium plus has more protons, it induces, and the electrons in the outermost orbital experience a greater effective nuclear charge, and thus the electrons found in sodium plus are held closer to the nucleus. So sodium plus has a smaller atomic radius than sodium, and additionally, it should have a smaller atomic radius than neon, because we have the same number of electrons as in neon, but we have a greater nuclear charge. We have more protons. So, in general, cations are smaller than their neutral element, and the greater the charge of the cation, the smaller the radius. Conversely, anions are larger than their neutral elements, and the greater the charge of the anion, the larger the radius. So just to do an example, so if we look at S2 minus, sulfur 2 minus has the same configuration as that of argon. However, if we compare sulfur and argon, we see that sulfur, if we look at the periodic table, we see that sulfur has 16 protons. So S2 minus would also have 16 protons, and argon has 18 protons. Now, because argon has more protons, argon is smaller, and as a result, sulfur conversely is larger, as the electrons present in sulfur experience a weaker nuclear attraction, they experience greater repulsions, and our atomic radius expands. Does this make sense to everyone? So S2 minus is larger than argon. So we can compare ions and isoelectronic species, and by looking at their charge and number of protons, we can determine which ion or atom is larger. Does that make sense to everyone so far? Sulfur 2 minus would be larger. Sulfur itself, neutral, is smaller. And that's the key distinction. The trends for ionic radius are slightly different than atomic radius because in ionic radius, we have a different relative number of protons and electrons. And as a result, when we add electrons, our atomic radius expands substantially. Does this make sense to everyone? Yeah, so sulfur has a larger atomic radius because it has less protons. And S2 minus has a larger ionic radius, a larger radius overall than argon because S2 minus has less protons relative to its electrons. That's exactly right. Yep. Perfect. Okay, so let's keep going now and let's look at a series of problems. So what I want you to do in the following example is I'd like you to write the electron configuration for each set of atoms and order each atom and ion in order of increasing atomic radius. So I'd like you to put the largest atomic radius at the right-hand side and the smallest atomic or ionic radius at the left-hand side. So let's spend about 5 minutes on this example and we'll discuss momentarily. And we'll discuss this example in about 4 to 5 minutes. And let's try to see some proposed rankings of each of these species in order of increasing atomic radius into the chat. And if you have any questions, don't be shy to ask them in the chat or unmute and ask the questions verbally. So when O2 minus, a negative charge indicates we're gaining electrons. Oh, no problem. And we'll discuss this example once I see a few responses in the chat, or in about 3 to 4 minutes. And if you have any questions, don't be shy to type them in the chat. This is the type of question and application problem that you'd be likely to see on an exam or quiz. So I want to make sure you're comfortable with these kinds of examples. And we'll discuss in about another 2 to 3 minutes. So it's not just the number of electrons, but it's the size of the outermost orbital compared to the number of protons. But in terms of your response in the chat, the logic is perfectly fine for this example. Yeah, you are correct in assigning lithium as the smallest. And we'll discuss this example. I'm going to give everyone a little bit more time in about another 2 to 3 minutes. I'd like to see some rankings of each of the atoms and ions in terms of increasing atomic radius. So that way I can provide some feedback. And in general, remember that anions are substantially larger than neutral atoms, and cations are typically very substantially smaller than neutral atoms. So aluminum 3+ is not quite the largest. It's going to be one of the smallest on this list. So anions are larger, cations are smaller. Negatively charged anions are larger, cations are smaller. Yes, so you're correct in that O2- is in fact the largest. So let's discuss this example to provide a little bit of clarity. So what I like to do first and foremost is I like to write the configurations. So lithium plus has a configuration of helium, so it's N equals 1. Sodium plus has the configuration of neon, which is N is equal to 2. Aluminum 3+ has a configuration of neon oops, let me find aluminum in the periodic table. Getting a little bit ahead of myself here. Let me pull up the periodic table. So aluminum also has the configuration of neon, N equals 2. Okay, neon has a configuration of neon, and O2- has a configuration of neon. Okay, so first and foremost, we consider sorting by N, outermost orbital size. So lithium plus is going to be the smallest because it has the smallest outermost orbital size. It's N equals 1 compared to N equals 2. The electrons for lithium plus in the N equals 1 shell are held closer to the nucleus. Now, looking at the remaining options, we're next going to consider the number of protons. So aluminum has 13 protons, sodium has 11, neon has 10, and O2- has 8 protons. In general, the larger the number of protons, the greater the attractive force to your outermost electrons, and the smaller your atomic radius or ionic radius. So of these options, if cations in general are smaller than the neutral species and anions, and the greater your charge, the smaller your radius, what is the next smallest species? What is the next smallest atom or ion? What's after lithium? Aluminum 3+, exactly right. Okay, and what's after aluminum 3+? What has the next greatest number of protons? More protons, smaller radius. What's the next smallest? Sodium plus, exactly right. Okay, now comparing neon and O2-. Yes, the more protons you have, the smaller your ionic radius because all of your species have the same number of electrons. They're isoelectronic in this series. So we can directly compare the number of protons to figure out the relative ranking for the atomic and ionic radius. So next we have neon, and finally our anion, O2- is the largest. So this is our complete ranking for each of our atoms and ions in order of increasing ionic radius. Does this make sense to everyone? Any questions on this example? So N, so if you look in the periodic table, you'll notice the N is equal to the period number. So for example, helium is in the first row, so its N is 1. Neon is in the second row, so its N is equal to 2 in the periodic table. Does that make sense? What do you mean by what's in the bracket? Yes, so it's the N value of your outermost orbital for your ions electron configuration. So we look at neon and helium because that is the N for our outermost orbital. That's exactly right. Does that make sense? Okay, perfect. So let's try another example just to make sure we're comfortable with this idea. I'd like you to write the electron configuration for each set of atoms and order each atom and ion in order of increasing atomic radius. And we'll discuss this example in about 5 minutes. And the responses I see in the chat look reasonable so far. And the ranking I see in the chat looks great so far. Let's try to get a few more responses and we'll discuss in about 3 to 4 minutes. And we'll discuss this example in about another 2 to 3 minutes. And the responses I see in the chat look great so far. Yep, and you're exactly right. And we'll discuss in about another 1.5 to 2 minutes. Yep, exactly right. And the logic I see in the chat looks perfect. Okay, so let's discuss this example. The responses I see in the chat look great. So first things first, I need to write my configuration. So I need to get out my periodic table. So phosphorus 3- has the configuration of argon. So that's N is equal to, whoops. N is equal to 3 since argon is in the third row. Selenium 2- has an equivalent configuration. Let me find selenium in my periodic table. It has the same configuration as krypton, which is N is equal to 4. Argon is N is equal to 3. Boron 3+ has the same configuration as helium. And sodium plus has the same configuration as neon. Helium is N equals 1. Neon is N equals 2. Okay, so first we sort by N value. So boron 3+ is the smallest. What's the next smallest? What has the next largest N value? Which is the size of our outermost orbital, which is the row in our periodic table for our isoelectronic species. So what's the next smallest? After boron 3+? Sodium plus, exactly. Okay, now looking at N equals 3, if we compare phosphorus and argon for our number of protons in phosphorus, we have 15. For our number of protons in argon, we have 18. So which species is smaller? Phosphorus or argon? Argon, yep, exactly. Argon has more protons, so the outermost electrons experience a greater attractive interaction. Phosphorus is the next smallest, and then finally we have selenium 2-. Now, what's really funny is that if you actually look up the atomic radius, phosphorus is almost larger than selenium. The moment you start getting above a 2- charge, your atomic radius just balloons dramatically as you have an excess number of electrons all experiencing repulsive interactions compared to a relatively small number of protons. Does this make sense to everyone so far? Okay. So we'll stop here for today, as I think we've covered a fair amount of lecture content, and I want to give everyone some time to integrate the material on your own and to work through some problems in the problem solving sets. So the plan is we're going to finish off this chapter tomorrow and then continue on with Lewis structures next class session. You'll see I'm almost done editing the lab exam and getting that all up and ready. Make sure you study your lab reports. As we lectured for a substantial amount of time, we'll push back some of the labs we had allocated for this period. Beyond that, are there any other questions that I can address? I'm just gonna end the recording so that way I can get that posted and processed.